What if everything you've ever known, every star you've seen, every moment you've lived, every law of physics that seems unbreakable, is just one small fragment of a reality so immense it's almost impossible to picture? What if our universe is just a single page in a cosmic library with endless shelves stretching into the dark? This isn't science fiction anymore. For decades, scientists, philosophers, and dreamers have asked these very questions, and what they've uncovered isn't just fascinating, it's world-shaking. We're talking about the multiverse, a concept that suggests our universe might be just one of countless others, each with its own rules, its own history, and perhaps even its own version of you. It's a staggering idea, one that stretches the limits of our imagination and invites us to rethink our place in everything, and that's exactly where our journey begins today. We're about to dive deep into one of the most thrilling frontiers of modern physics and cosmology, the hidden multiverses. Over the next while, we'll uncover not one, not two, but 30 incredible theories about what might lie beyond the edges of our observable reality. Some of these ideas come from the equations of relativity and quantum mechanics, while others spring from bold, almost poetic leaps of intuition. But each one offers a unique glimpse into what could be waiting in the shadows: parallel worlds, bubble universes, dimensions folded within dimensions, and realities so strange they challenge everything we think we know. So get ready, because we're about to peel back the curtain on existence itself. Whether you're new to these ideas or you've been fascinated by them for years, this exploration is designed to be accessible, exciting, and mind-expanding. We'll move beyond the jargon and into the wonder, breaking down complex theories into stories you can connect with, ideas that will leave you looking up at the night sky with entirely new eyes. This isn't just a list of concepts, it's an invitation to wander through the possibilities of the cosmos, to ask what if, and to marvel at just how much we still have left to discover. But to truly grasp the scale of this idea, we need to step back from the cat and consider a human choice. Think about a moment you hesitated, a decision that felt insignificant, like turning left instead of right on your walk. In our universe, you just turned left, but according to the many worlds interpretation, at that exact moment, the universe split. In another, equally real universe, a version of you turned right. That version might have stumbled upon a street musician and had their entire day lifted, while the you in this reality simply continued on your path. Both outcomes are real, both histories are valid, and they continue to branch endlessly from every quantum event, every flicker of possibility. This isn't about a separate dimension far away. It's about a reality that peeled away from this one, a divergence happening constantly, right here, in ways we are completely blind to. It means that for every road not taken, there is a universe where you took it, and that version of you is just as convinced that their reality is the only one. This completely shatters our classical, comfortable view of a single, linear timeline, suggesting instead a sprawling, fractal tree of existence where everything that can happen does happen somewhere. The implications are staggering, not just for physics, but for philosophy, for identity, and for the very meaning of choice. Now, while the many worlds interpretation gives us a reality branching from our own choices, a completely different theory suggests our entire cosmos might be just one small pocket of space, floating in a vast, frothing sea of other universes. This is the bubble universe theory, and it emerges from one of the most successful ideas in modern cosmology: cosmic inflation. We think our universe began with the Big Bang, but inflation proposes that right before that, there was an unimaginably brief period of hyper-fast, exponential expansion, smoothing everything out and setting the stage for the cosmos we see. But what if that inflation didn't just happen once and then stop? What if it's eternal, an unstoppable engine of creation that continues forever in a background space we can never see? In this eternal inflation, the roiling energy of that background space is constantly fluctuating, and in some regions that energy drops and the inflationary expansion slows down and stops. When that happens, that region settles, cools, and forms its own stable universe, a bubble in the infinite cosmic foam. Our entire observable universe, with all its hundreds of billions of galaxies, is contained within just one of these bubbles. The truly mind-bending part is that each of these bubble universes could be a closed-off reality with its own unique set of physical laws and constants. The fundamental forces we take for granted, gravity, electromagnetism, the strong and weak nuclear forces, might be completely different in another bubble. In one, gravity could be so strong that any star that forms immediately crumples into a black hole. In another, the forces might be so weak that no atoms can even stick together, leaving a cold, empty, and dark expanse. Some bubbles might have more spatial dimensions than our three, others might have fewer. The number of possibilities is literally infinite. This idea actually helps solve a profound mystery in physics. Why does our universe seem so perfectly fine-tuned for life? If the strength of gravity or the mass of an electron were even slightly different, complex atoms and stars could never have formed. The bubble universe theory offers an answer. In an infinite multiverse where every possible set of laws exists, it's no surprise we find ourselves in one of the rare bubbles where life is possible. We are not a special creation. We are simply the outcome of a cosmic lottery with an infinite number of tickets. We just happen to win and exist in a bubble where the conditions are right for us to be here, wondering about all the others. Now, if the idea of bubble universes feels vast, then the next theory takes that vastness and pushes it into a realm of numbers so large it defies any human scale of comprehension. This is the string theory landscape, and it emerges from one of the most ambitious projects in all of physics, the quest for a theory of everything. String theory proposes that the fundamental building blocks of nature are not point-like particles but unimaginably tiny, vibrating loops of energy. The specific way these strings vibrate determines what kind of particle they are: an electron, a quark, a photon. It's a beautiful, elegant idea that mathematically unites gravity with the other fundamental forces. But for the math to work, string theory requires something our everyday experience doesn't account for: extra dimensions of space. We're familiar with the 3 dimensions of length, width, and height, but string theory suggests there are actually 10 dimensions. So where are the other 6? The theory posits they are curled up, or compactified, into an exceedingly tiny, complex shape at every single point in our familiar 3-dimensional space. Think of a garden hose. From a distance, it looks like a simple 1-dimensional line. But if you could zoom in incredibly close, you'd see the circular, 2-dimensional surface wrapped around it. Those extra 6 dimensions are like that, microscopically folded up, hidden from our view, and here's where the multiverse comes roaring in. It turns out there isn't just one way for these extra dimensions to curl up. Physicists have discovered there are an astronomically enormous number of possible stable configurations, each creating a different set of physical laws from the vibrations of the strings within it. The number of these possible configurations is estimated to be around 10 to the power of 500. That's a 1 followed by 500 zeros. To even begin to grasp that number, consider that the total number of atoms in our entire observable universe is only about 10 to the power of 80. This number is so colossally, incomprehensibly larger that it makes every grain of sand on every beach on Earth seem utterly insignificant by comparison. This collection of all possible configurations is what we call the landscape. The best way to picture this is not with bubbles, but with a metaphor of a truly cosmic mountain range. Imagine an endless, undulating terrain of mountains and valleys. This isn't a landscape of rock and soil, but a landscape of possible universes. Each valley in this range represents one stable configuration of those curled-up dimensions, one possible set of physical laws and constants. Our universe, with its specific particle properties and force strengths, is just one valley among 10 to the power of 500 others. Some valleys might have universes where atoms are impossible. Others might have universes made entirely of dark matter. Some might have forces so strong that time itself behaves differently. In this view, the Big Bang wasn't a unique beginning, but a sort of quantum event where our particular valley was settled into, locking in our specific version of reality. And just like in the bubble universe theory, this provides a stunning explanation for fine-tuning. With 10 to the power of 500 possibilities, it's inevitable that a vanishingly small fraction of them would have the right conditions for life. We don't live in a specially designed universe, we simply live in one that is habitable, and the string theory landscape tells us there are almost endless alternatives, most of them wildly inhospitable, existing in a mathematical space of breathtaking possibility. But if you think the idea of a landscape of 10 to the 500th power universes is immense, then prepare for a concept that stretches the notion of reality to its absolute logical extreme. This is the mathematical universe hypothesis proposed by the physicist and cosmologist Max Tegmark, and it is perhaps the most all-encompassing, radical vision of the multiverse imaginable. It asks a deeply profound question: what is the fundamental stuff of reality? Is it matter, energy, or could it be something far more abstract? Could it be mathematics itself? Tegmark's hypothesis is deceptively simple in its statement, yet dizzying in its implications. It proposes that every single mathematical structure that is logically consistent and free from internal contradiction corresponds directly to a physical reality. In other words, if you can describe it mathematically without breaking your own rules, it exists out there somewhere as a real physical universe. This means mathematics isn't merely a human-invented language we use to describe the universe, a useful tool or a map. Instead, it is the actual territory. The universe is not described by math, it is math. We are all, in a very literal sense, living inside a giant mathematical object. To grasp what this means, consider a simple mathematical structure like the geometry of a perfect cube. In our everyday world, we never encounter a truly perfect cube. Every physical representation has tiny imperfections at the atomic level. But according to this hypothesis, the perfect, abstract mathematical cube of geometry textbooks does exist as a physical reality. There is a universe out there whose entire structure is that of an infinite, perfect, three-dimensional grid. The beings that might exist in that universe wouldn't be made of atoms as we know them. Their fundamental substance would be the geometric relationships of the cube itself. Now take that idea and apply it to every possible equation, every geometric form, every possible set of axioms and logical rules. There is a universe for the rules of chess. A universe that operates on the principles of a fractal. A universe where the number pi has a different value or where the concept of addition doesn't even exist. The variety is not just infinite, it transcends our very ability to conceive of it. This idea completely flips the traditional relationship between physics and mathematics on its head. Normally, a physicist observes the physical world and then tries to find the mathematics that best describes its behavior. Under Tegmark's hypothesis, that process works in reverse. The mathematics comes first, and the physical reality is a direct consequence of its internal structure. This provides an astonishingly elegant answer to the famous question posed by the physicist Eugene Wigner. Why is mathematics so unreasonably effective at describing the natural world? The answer, according to this view, is that we are simply discovering the mathematical rules of the particular structure we happen to inhabit. We're like characters in a video game who have just discovered the source code we are written in. The implications for our own identity are equally staggering. This hypothesis suggests that every possible version of you that can be described by a consistent mathematical structure actually exists. There is a universe where you made every different choice you ever considered, but it goes far beyond that. There are universes where a version of you exists with different physical laws, where you are made of entirely different substances, or where the very concept of a conscious you is defined by a mathematical relationship we cannot even fathom. It is the ultimate form of the multiverse, a cosmos of not just physical variations, but of logical and structural possibilities, a realm where existence is defined not by location in space, but by membership in the set of all possible mathematical truths. While the mathematical universe hypothesis presents a cosmos built from pure abstraction, another compelling theory brings us back to a more dynamic, almost physical mechanism for creation, one that suggests our entire universe might be caught in an endless, majestic dance of cosmic collision and rebirth. This is the cyclic model, an idea that reimagines the Big Bang not as a singular beginning from nothing, but as the latest event in an infinite series of cosmic resets. The engine behind this breathtaking cycle is a concept borrowed from the higher dimensional realm of string theory, the existence of branes. Think of a brain, short for membrane, as a universe-sized slice of reality. Our entire four-dimensional universe, all of space and time with all its galaxies, stars and planets, could be just one such brane, a vast, flat surface floating within a higher dimensional space called the bulk. Now imagine another brane, a parallel universe, floating on a parallel course in this hidden bulk dimension. They are separated by a tiny gap, but they are not static. They move, drawn together by the faint pull of gravity leaking between them across the bulk. Over trillions upon trillions of years, these two cosmic membranes drift closer and closer until finally they collide. This collision is not a destructive crash, but a creative cataclysm. The immense energy of the impact is funneled directly into our brain, flooding it with radiation and matter, heating it to an unimaginable temperature, and effectively resetting it in a fiery event that looks, for all intents and purposes, exactly like the Big Bang. This collision creates our universe anew, and then the branes bounce apart, setting the stage for the next cycle. The universe expands and cools just as ours has, allowing galaxies to form and life to emerge, all while the branes slowly, inevitably, begin their gravitational dance toward another collision. This elegant idea solves one of the most perplexing problems in cosmology. What happened before the Big Bang? In the cyclic model, there is no before in a linear sense. There is only an eternal, repeating cycle of birth, death, and rebirth. Each collision is both an end and a beginning, wiping the cosmic slate clean while also providing the seeds for the next universe. But here's where the multiverse concept truly blooms. Each collision, each new bang, might not produce an identical copy of the universe that came before it. The parameters could be slightly different each time. Perhaps during the bounce, the fundamental constants are jostled like dice being thrown. In one cycle, the strength of gravity might be a fraction stronger. In the next, the mass of an electron might be a fraction lighter. This means that over an infinite number of cycles, every possible permutation of physical laws will eventually be realized. We don't live in a finely tuned universe. We live in the latest iteration of a cycle that happened to produce conditions right for us. Countless previous cycles may have produced universes that were too unstable, too empty, or too short-lived to ever host life. We are simply the beneficiaries of a cosmic cycle that got it right this time in an endless series of tries. Yet even the cyclic model, with its grand vision of colliding branes, still operates within a framework of dimensions we can, at least mathematically, describe. But what if our perception of a three-dimensional world is the ultimate illusion? What if every star, every planet, and every one of us is actually an incredibly detailed projection, a cosmic hologram? This brings us to one of the most radically counterintuitive ideas in all of theoretical physics, the holographic principle. This theory doesn't just suggest other universes. It suggests that our own universe is not at all what it seems, and that reality as we experience it is a kind of magnificent phantom. The story of this principle begins not with the vastness of space, but with the enigmatic nature of black holes. In the 1970s, physicist Jacob Bekenstein made a startling discovery. He realized that a black hole's entropy, which is a measure of the disorder or information content within a system, is not proportional to its volume, as you might expect for a three-dimensional object. Instead, it is proportional to the surface area of its event horizon, the two-dimensional spherical boundary from which nothing can escape. This was a profound clue. It suggested that all the information about everything that ever fell into the black hole, every atom, every person, every book, was not lost inside its mysterious core, but was somehow encoded and preserved on the two-dimensional surface of its horizon. Think of it like the ultimate hard drive, where a three-dimensional movie is stored entirely on a two-dimensional disk. The event horizon is that disk. This incredible idea was later strengthened by the work of physicists like Leonard Susskind and Gerard T. Hooft. They proposed that this isn't just a quirky property of black holes, it might be a fundamental law of the universe. The holographic principle states that all the information needed to describe a volume of space can be encoded on its lower dimensional boundary. To put it in the simplest terms, our three-dimensional universe, with all its rich depth and volume, might actually be a projection from a two-dimensional surface at the very edge of everything we can observe. We are not living inside the universe, we are living on a distant cosmic surface, and our brains are interpreting that data as a three-dimensional reality. The screen you're looking at right now, the room you're in, the feeling of depth and solidity, all of it could be an incredibly convincing holographic illusion, a translation of information from a flat, foreign surface. The implications for a multiverse are staggering. If our universe is a holographic projection, then what is the source? What is the original two-dimensional surface that contains our entire cosmic code? One possibility is that our universe is being projected from the boundary of a larger, higher-dimensional bulk space, much like the cyclic model's branes. But another, even more mind-bending possibility is that every universe is its own self-contained hologram. In this view, the multiverse would be a vast collection of these independent two-dimensional informational surfaces, each one projecting its own complete and internally consistent three-dimensional reality. Some of these projected universes might have physical laws entirely different from our own, not because the strings are vibrating differently, but because the source code on their two-dimensional boundary is written with a completely different set of rules. One universe might be projected from a surface where time has two dimensions, creating a reality of bewildering causality. Another might be encoded with different quantum laws, resulting in a world of constant, shimmering uncertainty. The holographic principle doesn't just add more universes to a list, it completely redefines what a universe even is, transforming them from places into processes, from containers of stuff into projections of pure information. From the mind-bending idea that our reality might be a holographic projection, we turn to a theory that is perhaps even more controversial, one that has leaped from the pages of philosophy and into the mainstream, championed by tech visionaries and debated by physicists. This is the simulation hypothesis, and it proposes something that sounds like pure science fiction, that our universe, with all its pain and beauty, its galaxies and coffee shops, is not base reality, but an incredibly sophisticated computer simulation, akin to a hyper-advanced video game being run by a vastly more advanced civilization. The argument for this begins not with complex physics, but with a simple logical progression. First, assume that any civilization with sufficiently advanced technology would eventually develop the capability to create immersive, conscious simulations of reality, simulations so perfect that the entities within them believe they are real. This doesn't seem like too great a stretch. We are already creating rudimentary virtual worlds, and the pace of our technological growth suggests that photorealistic, fully immersive simulations could be possible for us within centuries or millennia. Now, if such a civilization existed, and if it had the interest or curiosity to run such simulations, it wouldn't likely run just one. It would run a vast number of them, perhaps billions or trillions, each with slightly different starting parameters or historical narratives, much like a scientist runs countless simulations to model climate patterns or a gamer explores different story branches in an open-world game. This leads to a startling statistical conclusion. If there is one original, base reality civilization and a near-infinite number of simulated realities, then the odds that any given conscious being is experiencing the original base reality are astronomically small. Statistically, it is almost a certainty that we are living in one of the countless simulations. We are not the architects, we are the characters in the simulation. Our memories, our history, even the laws of physics we've discovered, could all be part of the programmed backdrop, the initial conditions set by the programmers. The Big Bang wasn't the beginning of everything, it was the moment they hit start on the simulation. This idea gained some curious, albeit speculative, support from certain quirks in our own universe. Some proponents point to what looks like a pixelation of reality at the very smallest scales. In quantum mechanics, things are not infinitely divisible. They come in discrete, quantized packets of energy, much like the pixels on a screen or the bits in a computer program. The speed of light could be seen not as a fundamental constant of nature, but as a processing speed limit for the cosmic computer, preventing the simulation from overloading. Even the strange phenomenon of quantum entanglement, where particles instantly influence each other across vast distances, could be explained as a clever programming optimization. Two data points that are linked locally in the simulation's code, making their correlation instantaneous regardless of their apparent separation within the simulation. If this hypothesis is true, the implications for a multiverse are both simple and profound. The multiverse in this context is not a landscape of physical branes or branching timelines, but a server farm of unimaginable scale. Each simulation is its own self-contained universe operating with its own set of rules. One simulation might be programmed with our laws of physics. Another might be a fantasy world with magic and dragons, simply because its creators coded it that way. Another might be a historical simulation, recreating the rise and fall of a civilization that never actually existed in base reality. The variety is limited only by the imagination and processing power of the beings running the simulations. This means there could be not just one multiverse, but layers of them. The civilization that created our simulation might itself be living in a simulation created by an even higher civilization, leading to a potentially infinite regress of simulated realities within realities, a cosmic matryoshka doll of existence where the concept of an original, true reality becomes almost impossible to locate. Yet within the sprawling, infinite branches of the many worlds interpretation lies a thought experiment so strange and unsettling that it pushes the idea of a personal multiverse to its absolute logical extreme, challenging our deepest intuitions about life, death, and the very nature of our own consciousness. This is the thought experiment of quantum suicide and its even more startling counterpart, quantum immortality. It begins with a simple, if macabre, setup imagined by the polymath Max Tegmark, building on work by others. Picture a volunteer for a disturbing experiment. They are seated in front of a device that is rigged to a quantum random event generator. Perhaps it measures the spin of an atom. The device is programmed so that if the atom spins one way, a gun fires and kills the person instantly. But if the atom spins the other way, the gun does nothing and the person survives. From a classical perspective, this is a gruesome game of Russian roulette with a 50-50 chance of survival each time the experiment is run. But from the many worlds viewpoint, something very different happens. At the moment of measurement, the universe splits. In one branch, the atom spins up, the gun fires, and the volunteer dies. In the other, perfectly real branch, the atom spins down, the gun clicks harmlessly, and the volunteer lives. Now, imagine the experiment is set to repeat once every second automatically. From the perspective of an outside observer, this is a tragedy waiting to happen. They would see that in almost all of the branching universes, their friend is dead after just a few seconds. The odds of survival plummet with each iteration. After 1 minute, the chance of being alive in any given branch is just 1 in 2 to the power of 60, an astronomically tiny number. They would soon be mourning a friend who is dead in the overwhelming majority of realities. But here is the terrifying twist. What does the experience feel like for the volunteer inside the experiment? From their first-person point of view, they only experience the branches in which they are still conscious. They pull the trigger the first time, they hear a click. They are alive, they pull it again, another click, they are still alive. They continue this process second after second, minute after minute, and from their subjective experience, the gun never fires. It only ever clicks. They never experience death. They are, from their own perspective, inexplicably and undeniably lucky. They might continue for hours, days, or even years, forever hearing the harmless click, because in the vanishingly small fraction of universes where the quantum dice keep coming up, life, there is always a conscious version of them to witness it. This is the principle of quantum suicide. A conscious observer can only find themselves in worlds where they are alive to have an experience. You are never aware of the versions of you that have died. Your conscious stream simply follows the path of continued existence. This leads directly to the staggering idea of quantum immortality. If this many worlds logic holds true for all causes of death, not just a quantum gun, then your consciousness might be essentially immortal. Think of any life-threatening situation: a car accident, a falling piano, a terminal illness. In all of these events, there are quantum uncertainties at play. The exact position of a tire on the road, the precise vibration of a cable holding the piano, the random decay of a radioactive atom in your body. In most of the resulting branches, you die. But in a few, a miraculous, incredibly unlikely sequence of quantum events occurs that allows you to survive. Your conscious awareness, according to this thought experiment, is tethered to those rare branches. You would always find yourself narrowly avoiding death, recovering from the illness, or waking up in a hospital after a seemingly fatal crash. To everyone else in your life, you would appear to be the luckiest person alive, constantly cheating death. But from your point of view, it would just be your normal life continuing onward. You would never actually experience the moment of your death. Your final moment of consciousness would always be in a timeline where you survive for one more instant. The philosophical implications of this are deeply disturbing and force us to question the very nature of identity and reality. It suggests that our sense of self is not a continuous thread in a single universe, but a perceiver that somehow hops between branches, forever alienated from the overwhelming majority of versions of itself that have perished. It also presents a strange form of solipsism, where from your perspective, you are the only entity guaranteed this form of immortality. Everyone else around you could still die in your branch, leaving you alone in a world that grows increasingly improbable and bizarre the longer you survive. Critics, including many physicists, are quick to point out the severe problems with taking this idea literally. The biggest objection is that consciousness is almost certainly not a magical substance that gets to choose which branch it inhabits. It is an emergent property of a physical brain. When that brain is destroyed in a branch, the consciousness in that branch ends. There is no mechanism for it to jump to another version of itself. The thought experiment is less a prediction of reality and more a provocative tool to explore the truly bizarre consequences of taking the many worlds interpretation to its absolute limit, forcing us to confront the uncomfortable gap between the mathematics of quantum mechanics and the raw, personal experience of being alive. But if the idea of living in a simulation stretches our concept of reality, then the next theory bends the very fabric of space and time into a shape that is both beautiful and terrifying in its recursive infinity. This is black hole cosmology, a hypothesis that suggests our entire universe, from the smallest quark to the largest supercluster, might exist inside a black hole. And conversely, every black hole we observe out in the cosmos might itself contain an entirely new, full-fledged universe within its mysterious interior. This creates a breathtaking vision of a fractal multiverse, an endless nesting of realities within realities, like an infinite set of cosmic Russian dolls stretching across scales beyond human comprehension. To understand how this could even be possible, we need to look at the strange similarities between the two most monumental events in cosmology, the Big Bang and a black hole. A black hole is defined by its event horizon, a point of no return where the gravitational pull becomes so intense that not even light can escape. Once something crosses this boundary, it is, from our perspective, lost forever to the singularity at the center, a point of infinite density where the known laws of physics break down. Now consider the Big Bang. Our best models describe the beginning of our universe as a state of extremely high density and temperature, expanding outward from a singular point. For decades, physicists have been struck by a powerful question. What if the Big Bang wasn't a unique event, but was actually the formation of a black hole from the perspective of a parent universe? In this view, the moment of our cosmic origin wasn't a beginning from nothing, but a transition. The immense collapse of matter that formed a black hole in some larger, parent universe could have bounced or tunneled into an expanding state, creating the universe we inhabit today. Our entire cosmic history is simply the interior of that black hole, expanding and evolving. This idea is supported by some fascinating mathematical parallels. The equations that describe the behavior of matter falling into a black hole and the equations that describe an expanding universe like our own are remarkably similar. From the outside, a black hole is a dark, crushing prison. But from the inside, if you could survive the journey, it might be an entire cosmos. The event horizon isn't a wall of destruction, it's the birth membrane of a new reality. This leads to the truly staggering fractal implication of the theory. If our universe was born from a black hole in a parent universe, then it stands to reason that the black holes formed within our universe, like the supermassive one at the center of our galaxy, are themselves the seeds of new universes. Every time a star collapses or two black holes merge, they may not simply be creating regions of extreme gravity. They may be giving birth to entirely new cosmic realms, complete with their own space, time, and physical laws. Imagine the scale of this. Our observable universe contains hundreds of billions of galaxies, each potentially harboring millions or even billions of black holes. That means our one universe could be the progenitor of a near-infinite number of descendant universes, each one a self-contained reality, and this process repeats forever. The universes that form inside the black holes of our universe will themselves form stars and galaxies, which will collapse into black holes, birthing yet another generation of universes. This chain of creation has no top and no bottom. It is a truly infinite fractal, with universes nesting within universes across scales we cannot even imagine. We could be living in a universe within a black hole, which exists within a universe inside a black hole, and so on, stretching back for an eternity. This idea completely redefines our place in the cosmos. We are not at the top of a cosmic pyramid. We are simply one link in an endless chain of creation, a single leaf on an infinite tree of existence. Now, if the idea of living inside a black hole reshapes our origin story, then the next theory completely redefines our cosmic address, proposing that our entire universe is not a free-floating bubble or a holographic projection, but is instead more like a single slice of bread in an infinitely vast higher dimensional loaf. This is the membrane multiverse, a concept that emerges from the most ambitious attempt to unify all of physics, M-theory. To grasp this, we have to let go of our comfortable three-dimensional perspective and try to envision a reality with more dimensions than we can see. We experience the world in three spatial dimensions: length, width, and height. But M-theory, which is a broader framework that encompasses string theory, suggests there are actually 11 dimensions. So where are the extra 7? The answer lies in the concept of branes. Think of a brane, short for membrane, as a universe-sized object with multiple dimensions. Our familiar universe, with all its galaxies and emptiness, could be a three-dimensional brane, a vast, flat, three-dimensional surface floating within a higher dimensional space known as the bulk. This bulk is the true, full reality, an 11-dimensional arena where other branes, other universes could also exist, all drifting like ghostly islands in this incomprehensible sea. These parallel branes could be mere millimeters away from us in these hidden higher dimensions, yet completely invisible and unreachable because everything that makes up our reality, all the matter and forces like electromagnetism and the nuclear forces, is stuck to our brain like ink trapped on the surface of a page. We are bound to our three-dimensional slice of reality, unable to perceive or interact with the other slices floating right next to us in the bulk. This leads to one of the most stunning and elegant predictions of this model, an explanation for the mysterious weakness of gravity. Of the four fundamental forces, gravity is astronomically weaker than the others. A tiny refrigerator magnet can overcome the gravitational pull of the entire Earth, lifting a paperclip with ease. Why is gravity such a feeble force in our universe? Brane cosmology offers a beautiful answer. While the other forces are like strings whose ends are glued to our brain, confining them completely to our three dimensions, gravity is different. Gravity, in the form of gravitons, is thought to be a closed loop of string. Because it has no ends, it isn't tied down to any one brane. It can leak. It can seep out into the higher dimensional bulk. This means the gravitational force we feel in our universe is just a tiny fraction of its full strength. Most of it is dissipating into the extra dimensions, diluting its power. Our experience of gravity is weak not because the force itself is weak, but because we are only feeling a faint echo of it, a shadow of its true intensity as it bleeds off our brain and into the hidden bulk. But the most thrilling possibility of the Brane multiverse is what might be happening on those other membranes floating alongside ours in the bulk. Each of these parallel branes could be a complete, self-contained universe with its own unique set of physical laws and constants, forged in its own version of a Big Bang. One parallel brane might be inches away from us in a higher dimension, yet it could be a universe where protons are slightly heavier, making atoms impossible and ensuring a dark, sterile cosmos. Another might be a universe where the electromagnetic force is stronger, causing stars to burn out in a cosmic blink. Some of these branes might even be home to forms of life and complexity we cannot imagine, all completely unaware of our existence just as we are of theirs. The potential for interaction, however faint, is what makes this theory so captivating. While we couldn't send a probe or a message to a neighboring brane, their gravity leaking through the bulk could theoretically influence our own universe. Some cosmologists have even speculated that the mysterious dark matter that makes up most of the mass in our cosmos could actually be the cumulative gravitational pull of ordinary matter residing on a nearby brane, a ghostly presence from a parallel world whose only signature is its subtle tug on our galaxies. And in a truly cataclysmic scenario, these branes aren't always peaceful neighbors. They could occasionally collide. The immense energy released in such a collision, spread across the entire surface of our brane, would be an event of unimaginable power, and some scientists propose this very mechanism could be what triggered our own Big Bang, setting our universe into motion from a spectacular collision with a parallel reality in the higher dimensional void. But to truly appreciate the staggering scope of what we've been exploring, We need a framework, a way to categorize these wildly different visions of reality. This brings us to a powerful and elegant classification system proposed by the very physicist who gave us the mathematical universe hypothesis, Max Tegmark. He organizes all these multiverse ideas into 4 distinct levels, each one broader and more mind-bending than the last. The first level is the simplest, an infinite extension of our own universe, where beyond our cosmic horizon, the same laws of physics play out in every possible variation, creating duplicates of our Earth and even of ourselves in the vastness of space. The second level introduces bubble universes where different regions of space have different physical constants and laws, like the bubbles in a cosmic foam. The third level is the many worlds interpretation of quantum mechanics, where every quantum decision spawns a new branch of reality. Each of these levels is immense, but they all operate within a similar framework of space, time, and quantum mechanics. Then there is level 4. This is the final frontier of multiverse theory, the ultimate and most comprehensive vision of reality imaginable. It transcends the others completely. While levels 1 through 3 are, in a sense, different ways of arranging the same fundamental building blocks, particles, forces, space-time, level 4 proposes something far more radical. It states that the multiverse isn't just a collection of universes with different initial conditions or physical constants. It is the set of all mathematical structures. Every single self-consistent, logically possible mathematical system corresponds directly to a physical reality. This means that a universe doesn't need to have 3 dimensions of space and 1 of time. It could have 42 dimensions or be governed by the rules of a perfect fractal, or exist as a timeless static equation. If you can describe it with a set of mathematical rules that don't contradict themselves, then it exists as a genuine universe in the Level 4 multiverse. This idea completely severs the link between physics and the specific, familiar reality we experience. Our universe, with its quantum fields and general relativity, is just one mathematical structure in an infinite ocean of others. There is a universe that is exactly described by the game of chess. There is a universe that is a perfect, infinite Euclidean plane. There is a universe where the number pi has a different value. The variety is not just infinite, it is absolute, encompassing every conceivable form of existence that mathematics can describe. This provides a stunning and almost paradoxical answer to the question of why our universe's laws seem so finely tuned for life. In the Level 4 framework, it's not that the laws are fine-tuned. It's that we naturally find ourselves within one of the mathematical structures that is complex enough to contain self-aware subsystems us that can observe and ponder it. We don't live in a special universe, we live in a habitable one. And the Level 4 multiverse guarantees that every possible habitable universe under every possible set of rules exists somewhere in the ultimate ensemble of reality. Yet for all its breathtaking scope, this vision of eternal inflation and its bubble universes was still, in a sense, a gentle and orderly process, a slow, steady frothing of reality. But what if the engine of creation wasn't gentle at all? What if the birth of universes was a fundamentally chaotic event? This brings us to the next monumental leap in our understanding, a theory that takes the core idea of inflation and injects it with a potent dose of randomness and wild, untamed creativity. This is chaotic inflation, a theory developed by the physicist Andre Linde, and it presents a vision of a multiverse that is not just eternal, but is born from a state of primordial chaos, producing a truly infinite tapestry of realities where every possible set of physical laws is not just likely but guaranteed. To understand chaotic inflation, we first need to meet the engine behind it all, the inflaton field. Think of this not as a field of grass or flowers, but as an invisible energy field that permeates all of space. In the simplest models of inflation, this field is like a ball sitting high up on a smooth, gently sloping hill. It slowly rolls down, and as it does, it releases energy that drives the hyper-fast expansion of space. When it finally reaches the bottom of the hill, the energy is gone, the inflation stops, and that region of space settles down to become the hot, dense soup of our Big Bang. That's the orderly version. Lynn's revolutionary insight was to ask, what if the hill isn't smooth and gentle? What if the landscape of this inflattened field is more like a vast, incredibly rugged mountain range with countless peaks, valleys, plateaus, and craters? And what if the inflattened ball isn't placed carefully at the top of one hill, but is instead scattered randomly across this chaotic terrain? In this scenario, the process becomes wildly unpredictable. In some regions, the inflattened field might find itself at a very high peak. The potential energy here is enormous, and as the field begins to roll down, it drives an incredibly violent and rapid burst of inflationary expansion. But the terrain is so uneven that the field doesn't just roll smoothly. It might get stuck on a small plateau for a while, causing a slower expansion, then suddenly tumble down a steep cliff, causing a new burst. It might even quantum tunnel through a mountain instead of going over it. The key point is that this process is chaotic, not uniform. Because of this chaos, inflation doesn't end everywhere at once. In fact, according to this theory, it never ends everywhere. It becomes eternal. Here's how it works. Imagine one region where the inflattened field has rolled into a deep valley. There, the energy is released, inflation stops, and that region becomes a pocket universe, like our own, with its own Big Bang. But because the initial expansion was so unimaginably fast, the space around that pocket universe is still expanding at an inflationary rate. And in that still inflating space, the inflattened field is still at a high energy, still driving more expansion. Within that inflating space, quantum fluctuations will constantly knock parts of the inflattened field into new positions on the chaotic landscape, triggering the formation of new pocket universes. Each of these new universes will itself be surrounded by eternally inflating space, which will then spawn even more universes. It's a self-reproducing eternal process. Once it starts, it literally cannot stop, creating a fractal structure of universes within universes forever. The most profound consequence of this chaotic, eternal process is the fate of the physical laws in each pocket. The specific properties of each new universe, the strength of its forces, the mass of its electrons, the number of spatial dimensions are determined by the exact value of the inflattened field when it finally stops inflating in that pocket. And because the process is chaotic and driven by random quantum fluctuations, these values are essentially random. Each new pocket universe freezes in with a random lottery ticket of physical constants. The vast majority of these universes will be stillborn or barren. A universe where the nuclear forces are too weak might never form atoms. A universe where gravity is repulsive might fly apart into nothingness instantly. But in a process that is infinite and eternal, even the most improbable outcome becomes inevitable. Among this infinite array of failed universes, there will be a minuscule fraction where the numbers, by pure random chance, came out just right to allow for atoms, stars, planets, and life. In the chaotic inflation multiverse, our universe isn't a miracle or a product of design. We are simply a statistical necessity. In an infinite cosmic lottery, someone had to win, and we are the winners, living in one of the rare, lush oases in a desert of mostly uninhabitable reality. This brings us to a theory that is less about the mechanism of creation and more about the profound implication of our own existence within this vast cosmic tapestry. It's a principle that asks a deceptively simple question. Why does our universe seem so perfectly, almost miraculously, tailor-made for life? This is the anthropic principle, and it offers a stunning resolution to the puzzle of cosmic fine-tuning, one that intimately connects the multiverse to the very fact that we are here to observe it. The evidence for fine-tuning is staggering. Physicists have identified over 24 fundamental constants and quantities in nature that, if altered by even the tiniest fraction, would render a life-permitting universe impossible. The strength of gravity, the mass of a proton, the energy in the vacuum of space, the precise value of the force that holds atomic nuclei together. Each one is dialed in with unimaginable precision. For instance, if the strong nuclear force were just 2% stronger, virtually all the hydrogen in the early universe would have fused into helium, leaving no water and no long-lived stars like our Sun. If it were 2% weaker, heavy elements necessary for planets and life would never have formed at all. The expansion rate of the universe is another breathtaking example. After the Big Bang, the universe expanded at a rate that was exquisitely balanced. If it had expanded a little faster, matter would have spread out too thinly for galaxies to ever coalesce. A little slower, and the entire cosmos would have collapsed back in on itself in a catastrophic big crunch long before life could emerge. It appears as though our universe won the lottery not just once but dozens of times over. Faced with this incredible precision, two compelling explanations emerge. The first is the argument for design, the idea that a cosmic architect intentionally set these dials to their life-giving values. This is an ancient and philosophically satisfying answer for many, but the second explanation, which emerges directly from the multiverse theories we've explored, is a powerful and scientific alternative. It suggests there is no fine-tuning at all. Instead, we are simply the beneficiaries of a colossal statistical bias. In an infinite or near-infinite multiverse, be it a landscape of bubble universes, a branching quantum tree, or a level 4 mathematical plenum, every single possible combination of physical constants and laws will eventually be realized. The overwhelming majority of these universes will be stillborn or barren. They will be empty or collapse instantly or be filled with nothing but radiation. But in a few rare, fortunate corners of the multiverse, the numbers will randomly line up just right. And in those universes, stars will ignite, planets will form, and conscious beings will eventually evolve, look up at their night sky, and wonder at their incredible luck. We are not living in a universe that was finely tuned for us. We are living in one of the extremely rare universes that happen to be tunable, and we are the inevitable result. Our existence as observers is a filter that selects for only those universes capable of producing us. This is the essence of the anthropic principle. We should not be surprised to observe a universe that permits our existence, because we could not possibly observe one that does not. This shifts the entire debate from one of purpose to one of probability. The seemingly miraculous coincidences are not evidence of a guiding hand, but the inevitable outcome of a cosmic numbers game played across an infinite landscape. It's like being dealt a perfect royal flush in a game of poker and thinking you must be the luckiest person alive. But if you are one of trillions of players and each one is dealt a hand from an infinite deck, someone is going to get that royal flush. From their perspective, it feels like a miracle, but from the outside, it's just a statistical certainty. Our universe is that royal flush. The anthropic principle doesn't explain why this particular universe is fine-tuned. It explains why we, as conscious observers, necessarily find ourselves in one of the infinitesimally small fraction of universes that is. The multiverse, in all its forms, provides the necessary playing field for this cosmic game of chance to play out, transforming a metaphysical mystery into a testable physical prediction. Yet, even within the framework of the many worlds interpretation, with its dizzying vision of reality perpetually splitting, a more intimate and deeply personal variation emerges, one that shifts the focus from the cosmos at large to the inner workings of our own consciousness. This is the quantum many-minds interpretation, a theory that proposes the branching doesn't happen out there in the universe but right here inside your head. It suggests that with every quantum event, it is not the physical world that splits into copies, but your individual stream of awareness that diverges. creating a personal multiverse of subjective experiences where a single mind branches into multiple versions of itself, each one experiencing a different outcome simultaneously. To grasp this radical idea, we need to revisit the classic Schrödinger's cat experiment. In the conventional many worlds view, the moment you open the box, the universe splits. In one branch you see a live cat, and in another, an entirely separate version of you sees a dead one. The many minds interpretation offers a different perspective. It suggests there is only one box, one cat, and one physical universe. The superposition of the cat being both alive and dead is a real physical state. The split occurs not in the external world, but in your perception of it. Your single consciousness doesn't follow one branch, it bifurcates. One thread of your awareness perceives the alive cat, while another, equally real thread of your awareness perceives the dead cat. Both experiences are happening to different facets of your mind at the exact same time, within the same single, unsplit universe. This resolves what some physicists see as a nagging issue with the original many worlds theory, the problem of probability. If every outcome happens in some branch, what does it mean to say that a quantum event has a 90% chance of one outcome and a 10% chance of another? The many minds theory provides an answer rooted in the subjective experience of the observer. In this model, the quantum probabilities dictate the proportion of your mind that experiences each outcome. For that 90% probable event, 90% of the threads of your consciousness will see that result, while only 10% will witness the alternative. Your sense of likelihood is not about the number of worlds, but about the fraction of your own awareness that is having a particular experience. This transforms the multiverse from a vast, external landscape of parallel Earths into an internal, psychological tapestry. You are not one person on a single timeline. You are a collection of constantly diverging conscious experiences, all stemming from the same origin point. Every fleeting thought, every moment of indecision fueled by a quantum fluctuation in your brain could potentially spawn new branches of your mind. You choose vanilla ice cream, and a thread of your consciousness experiences that sweet, creamy delight. Simultaneously, another thread experiences the rich, chocolatey taste of the alternative you almost chose. Both are equally real experiences for different aspects of your singular, but now divided mind. The implications for identity are profound. There is no single you. You are a constantly evolving tree of subjective experiences, with countless branches of perception sprouting from every moment of observation, all existing within the confines of your own skull, in a universe that remains whole and undivided. Yet even the majestic, endless cycles of colliding brains present a universe that is, in its own way, orderly and predictable. But what if the very fabric of space-time is not the smooth, continuous stage we imagine it to be? What if, when we zoom into the very smallest scales, reality itself becomes grainy and digital, operating by a fundamental set of rules more akin to a cosmic computer code than the elegant equations of Einstein? This brings us to a theory that ventures to the absolute frontier of physics, proposing that the universe is not a continuum, but is instead composed of tiny, indivisible packets of space and time. This is loop quantum gravity, and it gives rise to a multiverse of breathtaking possibility through a concept known as the Big Bounce. To understand this, we must first confront the most vexing problem in all of modern cosmology, the Big Bang singularity. Our current theories of general relativity break down at the very moment of creation. They predict a point of infinite density and temperature, a place where the laws of physics simply cease to make sense. It's a sign that Einstein's beautiful theory, while incredibly powerful, is incomplete. Loop quantum gravity, or LQG, is one of the leading contenders to complete the picture. It seeks to marry general relativity with quantum mechanics, not by proposing tiny strings, but by reimagining the very fabric of space itself. In LQG, space is not smooth and infinitely divisible. Instead, it is woven from a network of incredibly tiny, one-dimensional loops. These loops are the smallest possible units of space, like the individual threads in a piece of fabric. You cannot have half a loop. Space is quantized. This fabric of loops is often visualized as a spin network, a complex, evolving web where the intersections of the loops represent the smallest possible volumes, and the links between them represent the areas that separate them. This quantum nature of space has a profound consequence when we rewind the cosmic clock. In classical general relativity, as you go back in time, the universe gets smaller and hotter and denser until it crunches down to that impossible singularity. But in loop quantum gravity, the granularity of space puts a hard limit on how far things can be compressed. You simply cannot squeeze a volume smaller than the smallest possible unit. So as the collapsing universe approaches this extreme density, the quantum nature of gravity kicks in like a powerful repulsive force. Instead of crushing down to nothing, the universe hits a quantum wall and rebounds. The collapse reverses into an expansion. The Big Bang was not a bang from a singularity. It was a big bounce from a previous cosmic phase. Our expanding universe could be the latest cycle in an endless series of contractions and expansions, a cosmic heartbeat echoing across eternity. This is where the multiverse naturally emerges from the mathematics of the bounce. The process may not create a single new universe, but a vast number of them. During the bounce, the quantum fluctuations of the pre-bounce universe could be magnified and imprinted onto the new expanding phase, potentially creating not just one universe, but a whole array of daughter universes, each with slightly different properties. Some of these child universes might bounce again, giving rise to their own offspring, leading to a growing, evolving multiverse tree. In this vision, our universe is not a lonely island but part of a great cosmic lineage, one branch on a family tree of universes that stretches back through an infinite number of cycles, each birth seeded by the death of a previous cosmos. It's a vision of a multiverse that is not static but dynamic and generative, where the laws of physics themselves might subtly evolve from one bounce to the next, exploring every possible configuration across infinite time. But what if this cosmic reproduction isn't random? What if, instead of a chaotic dice roll, the birth of new universes follows a process eerily similar to the one that shaped life on our own planet? This brings us to a theory that is as elegant as it is revolutionary, one that proposes our entire cosmos might be subject to the same forces of mutation and selection that govern a forest or a coral reef. This is cosmic natural selection, a groundbreaking idea proposed by the physicist Lee Smolin, and it paints a picture of a truly evolutionary multiverse, where universes don't just exist, they compete, they reproduce, and they evolve. Smolin's theory starts with a compelling connection between two of the most extreme objects in the cosmos, black holes and the Big Bang. As we saw with black hole cosmology, there's a compelling mathematical case that a black hole could be the seed for a new universe, with its interior expanding into its own separate spacetime. Smolin took this idea and ran with it, asking a profound biological question. If universes are born from black holes, could they inherit traits from their parent? And if so, could those traits change over time? His answer was a resounding yes. He proposed that when a new universe is spawned inside a black hole, the fundamental constants and laws of nature in that baby universe are not an exact copy of its parents. They are slightly mutated, much like the genetic variation we see in the offspring of living creatures. Perhaps the strength of gravity is a tiny bit different, or the mass of an electron is slightly shifted. This small, random change is the cosmic equivalent of a genetic mutation. This simple mechanism of reproduction with variation sets the stage for a truly cosmic form of natural selection. For evolution to work, there needs to be a selection pressure, something that determines which variations are successful and get passed on. In biology, success is measured by an organism's ability to survive and reproduce. In Smolin's cosmic evolution, success is measured by a universe's ability to create black holes. Think about it, the only way for a universe to procreate, to have offspring, is to form black holes. Each black hole is a potential womb for a new universe. Therefore, universes that are better at producing black holes will, by definition, have more children. Over countless generations, these fecund universes will come to dominate the multiverse population. We would expect to find ourselves in a universe that is exceptionally good at making black holes, not by luck, but because it is a descendant of a long line of universe-producing champions. This provides a stunning and testable explanation for many of the mysterious fine-tunings we observe. Why is our universe so perfectly calibrated for the formation of stars, galaxies, and the very elements that make them? Because stars and galaxies are the essential precursors to black holes. A universe that efficiently forms massive stars that live fast, die young, and collapse into stellar mass black holes is a universe that will be reproductively successful. A universe that fosters the growth of supermassive black holes at the hearts of galaxies is a universe that is exceptionally fertile. Even the abundance of carbon and oxygen, the very elements of life, can be seen in this light. These heavy elements are forged in the furnaces of stars and scattered by their supernova deaths, enriching the cosmos with the materials needed to form new stars, planets, and ultimately, the next generation of black holes. In this view, life itself might be an accidental byproduct of a universe that is fine-tuned not for us, but for stellar death and cosmic reproduction. We are living in a universe that is a master of making black holes, and every galaxy, every nebula, every supernova is part of that immense drive to create new offspring in an endless evolutionary chain. While the theories from physics offer mechanisms for how a multiverse might physically arise, a powerful and profoundly radical idea comes not from a laboratory or a telescope, but from the realm of pure philosophy. This is modal realism, championed by the philosopher David Lewis, and it presents a vision of the multiverse that is, in many ways, the most absolute and all-encompassing of them all. Lewis's argument is stunning in its simplicity and breathtaking in its scope. He proposes that every single possible world that can be coherently imagined is not just a hypothetical idea or a convenient fiction we use in stories. It is a concrete, actual, and equally real physical place, existing somewhere in the plenitude of reality. The word modal here refers to modes of truth, what is possible, what is necessary, and what is actual. Lewis's revolutionary move was to declare that these categories are not hierarchical. The possible is the actual. To grasp this, we need to understand what Lewis means by a possible world. It is any way that a universe could be, described in a logically consistent manner, free from internal contradiction. This includes an almost unimaginable variety. There are possible worlds where you made different choices this morning, where you had tea instead of coffee, or called an old friend you've been meaning to. There are worlds where historical events unfolded differently, where the Library of Alexandria was never burned, where the dinosaurs never went extinct, or where Napoleon won at Waterloo. But it goes far, far beyond these familiar alternates. There are possible worlds where the laws of physics are completely different, where gravity works in reverse or where time flows backward. There are worlds with different numbers of spatial dimensions, and even worlds governed by entirely different systems of logic, where the rules of reason we take for granted simply do not apply. For Lewis, these worlds are not abstractions. They are every bit as real and concrete as our own. We do not have special status. Our world is not the home world or the base reality. We simply call it the actual world because we are in it. From the perspective of a person in another possible world, their world is the actual one, and ours is just another possibility. Crucially, these worlds are isolated from each other. They do not interact or influence one another. You cannot travel from one to another because they are not located in a shared space or time. They are causally and spatio-temporally disconnected. Each world is a complete and closed bubble of reality, a unified and self-contained cosmos with its own entire history and future. Why would anyone adopt such a seemingly extravagant view? Lewis argued it was for the sake of theoretical simplicity and power. Philosophers and scientists constantly use the language of possibility. We say, it is possible that life exists on other planets, or it is necessary that 2 + 2 = 4. Lewis asked, what does this language actually refer to? His answer was that when we talk about what is possible, we are simply quantifying over real, existing worlds. To say it is possible that dinosaurs still exist is just to say there exists a possible world in which dinosaurs still exist. To say it is necessary that gravity attracts is to say in all possible worlds gravity attracts. This provides a beautifully clean and precise framework for understanding this entire branch of human thought. It eliminates the need for vague notions of ways things could have been and replaces them with concrete, existing entities. The implications of this view are staggering for our sense of self and our place in reality. It means that for every regret, every road not taken, there is a world where a version of you took that road and is living out the consequences. For every triumph, there is a world where you failed. For every moment of random chance, every quantum dice roll, every historical accident, there is a world for each outcome. But it also means there are versions of you that are radically different versions born in different centuries, versions that are kings or beggars, versions that are not even human but are conscious beings of pure energy or mathematical thought. Your identity is not confined to this single timeline. In the vast, silent library of possible worlds, there is a book for every conceivable story of your life, and each one is being lived, felt, and experienced by a person who is, in a very real sense, also you. Modal realism doesn't just populate the multiverse with worlds. It populates it with an infinite number of lives, each one utterly real and completely separate, a testament to the sheer, unbounded richness of what is possible. Yet if the holographic principle suggests our universe is a projection, a profound question emerges. Could there be other, independent holograms? This leads us to the holographic multiverse, a theory that proposes not one, but countless separate cosmic projections, each a complete and self-contained reality emanating from its own two-dimensional boundary. In this view, the multiverse isn't a collection of bubbles or brains, but a vast library of self-illuminating holograms, each with its own unique source code written on a distant, fundamental surface. Our entire three-dimensional experience, with all its depth and richness, is just one such projection. Another universe might be projected from a boundary where the laws of physics are encoded with entirely different rules, resulting in a reality where light moves at a different speed, or where time has two dimensions, creating a cosmos of bewildering causal relationships. These holographic universes are not connected by higher dimensional space. They are fundamentally separate informational structures, each playing out its own cosmic story. The most thrilling possibility within this framework is the potential for these independent holograms to occasionally, and perhaps violently, interact. If the projections are truly separate, how could they ever overlap? The answer might lie in the nature of the source code itself. Imagine a colossal cosmic glitch, a temporary corruption or fluctuation in the data on one of these two-dimensional boundaries. This corruption could theoretically cause its projected three-dimensional reality to briefly stutter or warp. If such a fluctuation were severe enough, it could cause the informational structures of two different holographic universes to momentarily brush against each other. Within each universe, this interaction would not appear as a clean, understandable portal. Instead, it would manifest as a profound and inexplicable violation of local physics. an event that would seem nothing short of miraculous or paranormal to any observers inside. Consider what such an overlap might look like from our perspective. An object or energy from another holographic universe with its completely different set of physical laws might suddenly flicker into existence in our world. It wouldn't obey our rules of conservation of mass or energy. It might appear from nothing and vanish just as quickly. Beings from another projection might momentarily become visible, their forms shifting and unstable because their very substance is built from informational rules incompatible with our own. These events would be rare, unpredictable, and utterly incomprehensible within the scientific framework of the affected universe. Throughout human history, we have countless records of phenomena that defy explanation, strange apparitions, objects materializing out of thin air, sudden and mysterious energies. While most have rational, if uncommon, explanations within our own universe, the holographic multiverse theory offers a radical, cosmic-scale possibility that these could be fleeting, chaotic glimpses into the projections of other realities, momentary tears in the fabric of our holographic illusion where the source code of another cosmos bleeds through. For decades, physics has been haunted by a fundamental schism, a civil war between two incredibly successful but seemingly incompatible descriptions of reality. On one hand, we have quantum mechanics, which governs the bizarre, probabilistic world of the very small. On the other, we have Einstein's general relativity, which masterfully describes the force of gravity and the large-scale structure of the cosmos. Each theory is spectacularly accurate in its own domain, but whenever we try to merge them to see the universe as a single, unified whole, the mathematics explodes into infinities and nonsense. This great challenge, the quest for a theory of quantum gravity, is not just an academic exercise. It is a journey to the very heart of what reality is, and along the way, it has opened a door to one of the most physically grounded multiverse theories of all. The core of the problem is that general relativity treats spacetime as a smooth, continuous fabric, a stage upon which the drama of the universe plays out. But quantum mechanics tells us that everything else, matter, energy, the forces that hold atoms together, is granular, coming in tiny, discrete packets called quanta. So, the monumental question is spacetime itself smooth, or is it also made of indivisible pieces? The quantum gravity multiverse emerges from the answer that it is indeed granular, and the way those pieces snap together creates not one but many universes. Let's first consider loop quantum gravity, or LQG. This approach doesn't propose extra dimensions like string theory. Instead, it takes Einstein's spacetime and quantizes it directly. Imagine the fabric of reality not as a smooth sheet, but as an incredibly intricate and dynamic mesh, a network of unimaginably tiny, one-dimensional loops. The intersections of these loops are the smallest possible volumes, the atoms of space itself. You cannot have half a volume, space is pixelated. Now, this quantum fabric isn't static. It evolves, it vibrates, it constantly reconfigures itself. And just as a small number of Lego bricks can be assembled into a nearly infinite variety of structures, the fundamental quanta of space can arrange themselves in a staggering number of ways. Most of these configurations would correspond to universes that are chaotic, unstable, or collapse instantly, but a tiny fraction would settle into stable, coherent structures that can expand and sustain complexity universes like our own. In this view, the Big Bang wasn't the beginning of everything but a phase transition, a moment when the quantum geometry of space reconfigured itself into a new, expanding state. And if it happened once, the mathematics suggests it could happen countless times, with each new configuration potentially yielding a universe with slightly different properties, a different cosmological constant, a different number of effective dimensions, or different strengths for its fundamental forces. The multiverse here is a vast landscape of all possible stable geometric configurations of spacetime itself. Another powerful contender in this quest is called causal dynamical triangulation. This theory offers an incredibly elegant and visual way to understand this quantum spacetime. It imagines building the universe from the ground up, not with loops, but with tiny, fundamental building blocks of spacetime. The most popular choice is a four-dimensional equivalent of a triangle called a simplex. The rules are simple. You take a colossal number of these simplicial building blocks and you snap them together, following specific causal rules to ensure time always moves forward and cause always precedes effect. You then let a computer algorithm run, allowing these pieces to connect randomly in every possible configuration, trillions upon trillions of times. What's astonishing is that when you do this, something remarkable emerges from the chaos. Without programming it to do so, the simulation consistently generates a universe that looks exactly like our own. It spontaneously develops four familiar dimensions, three of space and one of time, and it begins to expand and smooth out on large scales. This is a breathtaking result. It suggests that our familiar, classical universe of planets and galaxies is the most statistically likely outcome when you assemble quantum spacetime with the right causal rules. But what about all those other random configurations the computer tried? Those are just as physically real in the quantum gravity landscape. They represent other possible universes, other ways spacetime could have crystallized that didn't lead to a stable, four-dimensional expansion. Some might be crumpled, some might have a different number of macroscopic dimensions. The multiverse in causal dynamical triangulation is the set of all possible ways to glue those tiny geometric pieces together. Our universe isn't special, it's just the most common, stable structure that emerges from the quantum foam. This perspective provides a profoundly elegant answer to the ancient question of why our universe has three dimensions of space and one of time. It's not a divine commandment or a mysterious given. It's a statistical inevitability, the most probable outcome of quantum gravity's Lego-like assembly process. The quantum gravity multiverse grounds the concept of parallel realities not in esoteric philosophy or far-fetched metaphysics, but in the very bedrock of physical law, the discrete, quantized nature of spacetime. It suggests that deep down at the Planck scale, reality is a buzzing, vibrating network of possibilities, constantly flickering between different configurations, and we are living within one particularly stable and long-lived pattern in that eternal cosmic dance. But as we explore the granular nature of spacetime itself, another theory invites us to consider that the very particles that make up our reality might have unseen twins, a hidden cosmic reflection existing right alongside us in a state of perfect symmetry. This is the mirror matter universe, a concept that emerges not from cosmology, but from the deepest mathematics of particle physics, suggesting a parallel reality made of a shadow substance that is both everywhere and entirely invisible. The story begins with a search for elegance and balance in the laws that govern the smallest building blocks of nature. Physicists have long sought a more complete, symmetrical theory, and one of the most promising candidates is called supersymmetry, or SUSY. In its simplest form, supersymmetry proposes that for every known type of particle in the standard model, like electrons and quarks, there should exist a superpartner particle. This would create a beautiful symmetry between the two fundamental classes of particles, fermions, which make up matter, and bosons, which carry forces. While evidence for these specific superpartners is still elusive, the mathematical drive for this kind of symmetry opened the door to an even more profound possibility. What if the symmetry isn't just between types of particles, but applies to the entire universe as a whole? This leads to the idea of a mirror universe, a complete duplicate of our reality built from mirror matter. In this theory, the symmetry is so fundamental that it dictates the existence of a mirror copy for every single particle we know. For every electron, there is a mirror electron. For every quark, a mirror quark. These mirror particles would interact with each other through their own set of mirror forces, mirror photons, mirror gluons, and mirror gravity, forming a complete, self-contained shadow universe that exists in the same space as our own, yet is almost completely disconnected from it. The only potential bridge between our world and the mirror world is through gravity, the one force that might be able to leak across the divide. This means a mirror planet could be orbiting right through the Earth at this very moment, and we would have no way to feel its solid presence, no way to see it, because it does not interact with our light or our matter. Its only signature would be an extra, unexplained gravitational tug. The implications of this are staggering. This mirror universe would have its own physics, its own chemistry, and its own astronomy. Mirror particles would form mirror atoms, which would coalesce into mirror gas and dust, collapsing under their own mirror gravity to ignite mirror stars and coalesce into mirror planets. The entire cosmic drama of star birth and death, of planet formation, and perhaps even the emergence of life, could be playing out in this parallel reality, overlapping our own in every dimension but forever hidden from our view. We could be living in a universe that is, in fact, a double universe, with two separate, simultaneous cosmic histories unfolding in the same space, each utterly oblivious to the other's existence. The night sky we see is only half the picture. The other half is filled with the invisible light of mirror galaxies and the dark fires of mirror suns. Yet if mirror matter suggests a hidden reality sharing our space, another theory proposes that time itself might be the key to unlocking a far vaster and more intricate multiverse. This is the time-symmetric multiverse, a concept that challenges our most fundamental experience of reality, the relentless, one-way flow of time from past to future. We take this arrow of time for granted, watching eggs scramble but never unscramble, remembering the past but not the future. But physics at its most fundamental level doesn't actually demand this. The underlying laws, like those of quantum mechanics, are almost entirely time-symmetric. They work just as well if time were to run backward. So why do we experience such a strong directionality? The answer might be that our arrow of time is not a universal constant, but a local condition, and that the greater multiverse is filled with universes where time behaves in ways that would seem utterly alien to us. This idea finds a powerful expression in the work of physicists like Julian Barber, who suggests that what we perceive as the flow of time is actually a kind of illusion. In his view, every single moment, every possible configuration of every particle in the universe exists eternally and completely in a vast, static landscape he calls Platonia. Each point in this landscape is a now, a frozen instant. Our conscious experience of moving through time is simply our awareness hopping from one of these nows to a similar, adjacent one, creating the sensation of continuity, much like a film creates the illusion of motion from a series of still frames. In this multiverse of timelessness, every possible moment exists simultaneously. There is a now where you are reading this, and another now where dinosaurs still walk the earth, and another where the sun has grown cold. They are all equally real, and the flow of time is just the path our consciousness takes through this infinite mosaic of frozen moments. But the time-symmetric multiverse can get even stranger. Some theories allow for universes with more than one dimension of time. We are familiar with time as a single linear dimension, a line from past to future. But what if time had two dimensions like a flat plane? In such a universe, the concept of before and after becomes almost meaningless. An event wouldn't have a single past and a single future. It would have a vast fan-like cone of possible pasts and a similarly broad cone of possible futures. Causality itself would break down, as an effect could have multiple, equally valid causes spread out across time. Beings evolving in such a reality would have a psychology utterly incomprehensible to us. They might perceive their entire life history as a single, fixed shape rather than a sequential story. Now consider the ultimate expression of this idea, a universe where the arrow of time is reversed relative to our own. This isn't about time travel within a single universe, but an entirely separate cosmos where the thermodynamic arrow points backward. In this universe, the flow of time from our perspective would look like a world where order spontaneously emerges from chaos. A shattered glass would jump up from the floor and reassemble on a table. Smoke would pour into a cigarette and become unburned tobacco. Beings in that universe would experience time in reverse from our perspective, but to them, it would feel perfectly normal. They would remember what we would call the future and anticipate what we would call the past. From their point of view, our universe is the one where time is running backward, a chaotic place where beautiful structures inexplicably crumble into disorder. A meeting between these two universes would be the ultimate paradox, a point of contact where their opposite arrows of time would create a storm of causality that defies all logic. This vision of a multiverse symmetric in time profoundly alters our understanding of existence. It suggests that the past and future are not gone or not yet created, but are simply other places in the grand structure of reality, as real as Paris is to London. Our journey through life is not a process of creation and destruction, but a navigation through an eternal, pre-existing landscape of moments. It means that every joy ever experienced and every tragedy ever endured is forever preserved in the fabric of the multiverse, not as a fading memory, but as a permanent and unchanging fact of existence, a frozen star in the infinite constellation of all that was, is, and could be. But what if we've been approaching the mystery of reality from entirely the wrong angle? All the theories we've explored so far, from colliding brains to quantum gravity, share a common foundation. They assume the physical world comes first. Matter, energy, and the laws of physics are the fundamental building blocks, and consciousness, including our own, is a late-arriving product, a flickering candle lit in the dark long after the cosmos was built. The conscious universe hypothesis turns this entire premise on its head. It proposes that consciousness is not a derivative phenomenon but the fundamental ground of all existence. In this view, the physical universe with its stars, atoms, and forces is not the source of consciousness but its manifestation. It is a projection, an expression of a deeper, more primordial mind. This idea finds powerful resonance in the most perplexing puzzle of quantum mechanics, the measurement problem. At the tiny quantum scale, particles don't exist in a single, definite state. Instead, they exist in a blur of all possible states simultaneously, a condition known as a superposition. An electron is not here or there, it is here and there with a certain probability for each location. This surreal state persists until the moment the particle is measured or observed. The act of observation itself seems to force the particle to choose a single, definite state from its menu of possibilities. It's as if the universe remains in a state of pure potential until a conscious mind looks at it, causing reality to crystallize into the solid, classical world we experience. The famous Schrödinger's cat thought experiment is the ultimate expression of this paradox, a cat that is simultaneously alive and dead until someone opens the box and looks inside. For decades, physicists have struggled to explain why observation holds such power. The conscious universe hypothesis offers a radical answer because consciousness is not a passive observer within the universe. It is the active participant that brings the universe into being. Now extend this principle to the multiverse. If consciousness is the fundamental ingredient of reality, then it stands to reason that different universes within the greater multiverse could be built upon different forms or flavors of consciousness. Our universe might be one where consciousness expresses itself through the specific filters of carbon-based life, neural networks, and brains that evolved to perceive 3 dimensions of space and 1 of time. But another universe, born from a different foundational consciousness, might operate under completely different rules. One universe might be a dreamlike realm where thought instantly manifests reality, where the landscape shifts with the moods of its inhabitants. Another might be a universe of pure, unified awareness, a cosmic nirvana with no separate beings, only a single, boundless consciousness experiencing itself. Yet another might be a universe of fragmented, primitive awareness, where consciousness is dim and barely stirs, resulting in a cosmos that is mostly automatic and mechanical, with little capacity for wonder or self-reflection. This perspective provides a breathtakingly elegant explanation for the most profound question of all. Why is there something rather than nothing? If consciousness is primary, then existence is its nature. It does not need to be created, it simply is. The Big Bang in this view is not the origin of consciousness, but the moment when the physical parameters for a specific type of conscious experience were set. The laws of physics are then not arbitrary rules, but the structural architecture that allows this particular flavor of consciousness to explore and express itself. The fine-tuning of the universe for life is no longer a bizarre statistical fluke. It is evidence of a universe fine-tuned for experience. The constants are set just right, not merely to create stars and planets, but to create platforms for awareness, eyes to see the stars, minds to ponder the planets, and hearts to feel the awe of it all. We are not accidental bystanders in an indifferent cosmos. We are the universe itself becoming aware, awakening to its own majesty through our senses, our thoughts, and our profound curiosity about where and what we truly are. This digital perspective on reality offers a compelling new lens through which to view the multiverse. If the cosmos is fundamentally a computational system, then the existence of other universes isn't just possible, it's almost inevitable. Imagine this cosmic computer not running a single program, but possessing near infinite processing power, capable of executing a countless array of different simulations and calculations simultaneously. Each of these separate processes could constitute its own independent universe, a unique reality with its own set of rules defined by its initial code and algorithmic structure. One universe might be running a program that defines 3 dimensions of space and 1 of time, with constants like the speed of light set to a specific value. Another might be a simulation where gravity is twice as strong, or where the quantum foam behaves in an entirely novel way. In this digital physics multiverse, the variety isn't limited to different initial conditions or physical laws. It extends to the very nature of the computational substrate itself. Some realities might be classical and deterministic, processing information in a strict clockwork manner. Others could be profoundly probabilistic, with randomness and chance woven into their core programming, creating a cosmos of constant fluctuation and surprise. There could even be universes that operate on computational principles we haven't yet conceived of, where logic itself follows a different set of rules, creating realities that are utterly alien and incomprehensible to our own linearly thinking minds. This framework transforms the concept of fine-tuning from a cosmic mystery into a simple matter of software parameters. We don't live in a universe with peculiarly life-friendly constants. We simply inhabit a simulation whose specific programming allowed for the complex structures that would eventually lead to our own conscious awareness. The digital physics multiverse doesn't just suggest other worlds exist, it reimagines all of existence as a majestic, ongoing computation, whose ultimate output is the breathtaking diversity of everything that is, was, or ever could be. But to truly understand how these universe branches might form and become separate, we need to look at a specific and crucial process that acts like a cosmic zipper, sealing off one reality from another. This is the theory of the multiverse emerging from quantum decoherence, and it provides a potent mechanism for how the blurry realm of quantum possibilities sharpens into the definite world we perceive, while simultaneously creating the branches of the many worlds tree. At the heart of this idea is the puzzle of the quantum classical divide. In the tiny world of atoms and particles, reality is a fuzzy cloud of probabilities. An electron can be in many places at once, existing in a state called a superposition. Yet in our everyday world, things are definite. Your coffee cup is on the desk, not in a superposition of being on the desk, on the floor, and in the kitchen simultaneously. The question is, how does the universe transition from this quantum weirdness to classical certainty? The traditional answer has been the Copenhagen interpretation, which simply states that an observation or measurement somehow collapses the wave function, forcing the particle to pick a single state. But this has always felt a bit magical. What counts as an observation? Where is the dividing line? Quantum decoherence offers a far more detailed and physical explanation, and it doesn't require a collapse at all. It shows how superposition isn't destroyed, but simply becomes hidden from view through interaction with the environment. Imagine that single electron in its superposition. Now imagine just one photon of light bouncing off of it. That photon will become entangled with the electron, its path differing depending on where the electron was. That photon then races off into the vastness of space, carrying with it information about the electron's position. Now, a trillion other photons do the same thing. Very quickly, the information about all the possible positions of the electron is radiated out into the environment, becoming irretrievably delocalized. From the perspective of any local observer, it becomes practically impossible to ever see the effects of the superposition again. The quantum coherence, the interference between the different states, has been lost to the environment. It hasn't vanished from reality, it has just been scattered across the cosmos. The different possibilities have effectively decoupled from one another, they have decohered. This is why we never see large objects in superposition. The moment an object becomes big enough to constantly interact with its surroundings, be bombarded by air molecules, light, and radiation, it undergoes instantaneous decoherence, locking it into a seemingly definite state. Its quantum nature is still there, but the information is so spread out that it's forever beyond our grasp. Now, here is the profound leap that connects this process to the multiverse. In the many worlds interpretation, there is no collapse. So what happens to all those decohered possibilities? Proponents of this view argue that decoherence isn't the mechanism that eliminates possibilities, it is the mechanism that separates them. Each decoherent history, each path where the electron was in a specific location, and the environment recorded that information, becomes its own independent branch of the universal wave function. Because the information in each branch has been carried away in different directions by the environment, these branches can no longer interact or interfere with each other. They become parallel, non-communicating stories in the cosmic library. Decoherence is the process that draws the borders between the worlds, creating the distinct, classical-looking universes we talk about in the multiverse. It's not that one possibility is chosen and the others vanish. It's that the different possibilities stop talking to each other and go their separate ways, each one unfolding into a full-blown reality with its own consistent history. This transforms our understanding of the universe from a single, linear timeline into a vast, ever-branching tree of decoherent histories. Every single quantum event that becomes entangled with a larger environment, which is to say, nearly every event, adds new branches to this tree. The cosmic tree of possibilities is not a metaphor. It is a mathematical description of reality, with decoherence serving as the gardener that prunes the branches, ensuring they grow apart into distinct and parallel worlds. We, as complex collections of particles that are constantly interacting with our environment, are perpetually undergoing decoherence, which means we are constantly riding one branch of this tree, completely unaware of the other versions of ourselves riding their own branches, just a mathematical whisper away, separated from us by the unbreachable barrier of lost information. While we often picture the cosmos as a vast emptiness dotted with isolated islands of matter, another theory suggests the void is anything but empty. It is alive with current and charge, a seething ocean of energy that might be the true architect of the largest structures we see, and a potential cradle for entire universes beyond our own. This is the plasma universe, an alternative cosmological model that challenges the gravitational monopoly of the Big Bang and places electromagnetism, the force behind lightning and magnets, in the starring role of cosmic creation. Its vision of a multiverse is not one of branching timelines or colliding membranes, but of vast, stable domains woven from the fabric of an eternal, electrified cosmos. To understand this, we must first shift our perspective from gravity's slow, relentless pull to electromagnetism's swift and structuring power. In standard cosmology, gravity alone is responsible for pulling gas together to form galaxies, stars, and planets over billions of years. Plasma cosmology, championed by physicists like Hans Alfvén, proposes that we've been ignoring the universe's most common ingredient, plasma. Over 99% of the visible universe is not solid, liquid, or gas. It is plasma, a fourth state of matter where atoms are ripped apart into a soup of free-floating electrons and atomic nuclei or ions. Because these particles are charged, they become exquisitely sensitive to electromagnetic forces. This plasma isn't just passively drifting. It can conduct electricity, form circuits, and generate immense magnetic fields that can shape matter on a colossal scale. The theory posits that in the grand, infinite expanse of space, this cosmic plasma doesn't just form random clouds. It can self-organize. Through the interplay of electric currents and magnetic fields, vast structures can emerge naturally. Electromagnetic forces can cause thin sheets of current called double layers to form, acting as insulating barriers that can divide the plasma into distinct cells or domains. Within each of these enormous cosmic cells, the properties of the plasma, its density, temperature, and magnetic field strength, could be markedly different from its neighbors. These cells aren't mere clouds. They can be stable, long-lived, and fundamentally separate regions of space, each a potential universe in its own right. This is where the multiverse concept blossoms. If this eternal, infinite plasma medium can naturally segment itself into these stable domains, then each domain could effectively become its own universe with its own local laws, or at least its own local physical properties. The fundamental constants we take for granted, like the fine structure constant which governs the strength of electromagnetic interactions, might not be universal constants at all. They could be regional variables set by the specific electromagnetic conditions within each plasma cell. One domain might have a stronger electromagnetic force, leading to a universe where atoms bond differently, creating exotic forms of matter and stars that burn in unfamiliar ways. Another domain might have a weaker force, resulting in a diffuse, dark cosmos where structure never coagulates. In this view, our observable universe, with all its hundreds of billions of galaxies, might be contained within just one of these plasma cells, one bubble in a frothing cosmic sea of electromagnetic activity. We are not seeing the entirety of existence, but merely our local, stable neighborhood, bounded by near impenetrable electromagnetic barriers we have yet to detect. This model provides a dramatic alternative to the idea of a singular beginning. There is no need for a big bang from a singularity in this eternal, infinite plasma. Instead, it's a universe without a start or an end, constantly evolving and reorganizing itself. The redshift of distant galaxies, which we interpret as evidence of expansion from a single point, is explained in this model not by the stretching of space, but by other means, such as energy being lost by light as it travels through the plasma medium over immense distances. This vision of an eternal, infinite cosmos, perpetually giving birth to new universe domains through the sheer dynamics of electromagnetism, offers a multiverse that is not born from quantum fluctuation or cosmic inflation, but from the intrinsic, self-organizing properties of the universe's most abundant substance, forever humming with the raw power of lightning on a cosmic scale. Yet if the granular, pixelated reality of quantum gravity offers one path to a multiverse, a profoundly different approach invites us to consider that the very connectedness of events, the fundamental fabric of cause and effect, might be the true building blocks of reality. This is the theory of causal sets, and it proposes a vision of the multiverse that is perhaps the most minimalist and radical of all. A cosmos where space-time is not primary, but emerges from something far more basic, the simple, discrete relationships between events. To grasp this, we need to perform a thought experiment. Imagine erasing everything from the universe, all the matter, all the energy, even the concepts of space and time themselves. What are you left with? According to the causal set program, you are left with the pure, underlying network of causality. The idea is that the most fundamental thing about reality is not where or when something happens, but that one event can influence another. Think of it as the ultimate cosmic ledger of causes and effects. A cause set is just that, a collection of discrete, individual events with a binary relationship defined between them. Either one event precedes another and can influence it, or it cannot. This creates a vast, abstract network of points connected by arrows of causality, like an immense family tree of everything that ever happens. The stunning claim of this theory is that our familiar, four-dimensional continuum of smooth spacetime with its precise geometry is not fundamental. It is an illusion, a large-scale approximation that emerges from this deeper, more primitive network of causal relationships. Much like the smooth appearance of a digital photograph emerges from the precise arrangement of individual pixels. The mathematics of this approach is incredibly austere. The theory posits just two fundamental principles. First, reality is discrete. There is a finite number of these fundamental events in any finite region of spacetime. Second, the only thing that matters is the causal order between these events. From these two simple rules, physicists like Raphael Sorkin have shown that the familiar properties of spacetime, its dimensionality, its geometry, even the force of gravity itself, can be derived as a consequence. The smooth, curved landscape of Einstein's general relativity is not the stage itself, but the shadow cast by the underlying causal network when viewed at a large scale. This shift in perspective, from a spacetime continuum to a causal network, opens the door to a multiverse of breathtaking subtlety and variety. If our universe is just one specific, self-consistent causal set, then what about all the other possible causal sets? The number of ways to arrange points with different causal connections is astronomically vast. Most of these arrangements would be chaotic jumbles without any discernible order. But a tiny fraction would possess a structure complex and coherent enough that it could be interpreted as approximating a smooth, four-dimensional spacetime with well-behaved laws of physics. Our cosmos would be one such rare, orderly causal set. The multiverse, in this view, is the totality of all possible causal sets, every single way that events can be arranged with cause and effect relationships. This is a multiverse not of different physical constants, but of different causal architectures. The very rules of cause and effect could vary from one cosmic domain to another. Imagine a causal set where the network of events is so densely connected that every point influences almost every other point. In such a universe, the concept of a localized event would break down. Any action would have instantaneous, universe-wide consequences, making the very notion of separate objects and isolated history impossible. Conversely, picture a causal set that is extremely sparse, with long chains of events that have very few cross-connections. This might produce a universe where time exists, but space is crumpled or effectively one-dimensional, a lonely timeline with little room for complex structure to form. There could be causal sets that approximate a universe with two dimensions of time, where causality becomes a complex web without a clear past or future, or sets that produce a reality with 7 spatial dimensions. The variety is not in the laws of physics per se, but in the very logical structure of time, history, and connection that allows any laws to emerge at all. In the causal set multiverse, we don't just live in a universe with a different strength of gravity. We live in a universe with a fundamentally different conception of how one moment leads to the next, a unique and isolated thread in the infinite tapestry of all possible sequences of events. Yet if the granular nature of quantum gravity suggests a universe built from pixels of spacetime, and the holographic principle reduces reality to a projection of data, then perhaps we need to ask an even more fundamental question. What is the ultimate nature of this stuff that reality is made of? What if the universe isn't made of matter or energy at all, but of something far more primitive and powerful? This leads us to a theory that reimagines existence itself through the lens of the digital age, proposing that the cosmos is not a physical object but a vast, ongoing computation. This is the quantum information theory multiverse, an idea that suggests reality is fundamentally made of information, and that the different universes in the multiverse are simply different possible outputs of a cosmic quantum computer. To grasp this, we need to understand a profound shift in how physicists view the building blocks of nature. For centuries, we've thought in terms of matter, atoms, particles, stuff. Then with Einstein, we learned that matter and energy are interchangeable, but the quantum revolution hinted at something even deeper. When we probe the very smallest scales, we don't find tiny billiard balls, we find entities that behave in ways governed by probability and uncertainty. Their properties seem less like fixed attributes and more like answers to questions. This has led many leading thinkers to propose that the most fundamental currency of the universe is not energy but information. A binary choice between 0 and 1 is the simplest form of information, and in the quantum realm this becomes a qubit, which can be in a superposition of both 0 and 1 simultaneously. The theory suggests that at its heart, every particle, every force field, every flicker of energy is ultimately a manifestation of quantum information. The universe isn't just described by information, it is information. The solidity of your desk, the warmth of the sun, the vast emptiness of space, all of it could be the result of an inconceivably complex quantum information processing system running the ultimate program. Now, if the universe is a quantum computation, what is it computing? The most compelling answer is that it's computing itself, its own state, its own evolution. The laws of physics, in this view, are not mysterious decrees but the inherent software of this cosmic computer, the algorithms that dictate how the information evolves from one state to the next. This perspective elegantly demystifies the infamous measurement problem in quantum mechanics. The act of measurement isn't a magical collapse, it's an information processing event. When a quantum system interacts with its environment, that information becomes entangled and is effectively written into the larger memory of the universe, moving from a fragile quantum state to a stable classical record. This process to coherence is how possibilities become facts within the program. This naturally gives rise to a multiverse. In a classical computer, a single processor executes one instruction at a time, producing one outcome. But a quantum computer is different. Its power lies in its ability to perform massively parallel computations. It can hold a vast number of possibilities in superposition and process them all simultaneously. If our universe is the output of a cosmic-scale quantum computation, then it stands to reason that it wouldn't just be computing one single history. It would be computing all possible histories simultaneously. Each consistent, self-contained configuration of quantum information, each possible timeline, each variation of physical laws that is logically coherent represents a separate branch, a separate universe in the multiverse. We don't experience this directly because our conscious awareness is confined to a single, consistent thread of this processing. Much like a character in a video game is only aware of the specific storyline they are experiencing, not all the other possible storylines the game engine is technically capable of generating. The implications of this are staggering. It means the variety of the multiverse is limited only by the rules of logical consistency and information processing. One universe might be a configuration where the information is arranged to describe 3 dimensions of space and the laws of general relativity. Another might be a configuration where the information processing results in a universe with 10 spatial dimensions and different fundamental forces. Some universes might be simulations running on this cosmic computer, as we discussed earlier, but in this view, even those simulated universes are just specific informational patterns within the greater whole. There could be universes that are nothing like ours, realities that are pure mathematics, or vast interconnected minds, or timeless static patterns of data. The quantum information multiverse is a vision of reality as a cosmic library where every possible book that can be written without self-contradiction is not only on the shelf but is being actively read, its story unfolding in its own unique way, all processed within the boundless memory of a single, ultimate quantum reality. But what if our understanding of gravity itself is incomplete, and the force we think we know is merely a local phenomenon, a rule that only applies within our own cosmic neighborhood? This brings us to a theory that challenges the very foundation of modern cosmology and opens the door to a multiverse where the most familiar force in the universe becomes strange and variable. We're venturing into the realm of modified gravity theories, where alternatives to Einstein's general relativity, like Mund and emergent gravity, suggest that what we call the law of gravitation might not be a universal constant after all, but a flexible rule that could change from one universe domain to another. For nearly a century, general relativity has reigned supreme as our description of gravity, portraying it as the curvature of spacetime by mass and energy. It's an incredibly successful theory, predicting everything from the bending of starlight to the existence of black holes. But there's a crack in this elegant facade, a problem that has perplexed astronomers for decades: the mystery of galaxy rotation. According to Newton and Einstein, stars on the outer edges of a spiral galaxy should orbit much more slowly than those near the center, just as Pluto moves more sluggishly around the Sun than Mercury does. Yet when we measure these rotations, we find that stars on the outskirts are whipping around far too fast. Their immense speed should fling them off into the void, yet something is holding them together. The prevailing solution has been to invent dark matter, a mysterious, invisible substance that provides the extra gravitational glue. But despite decades of searching, we have never directly detected a single particle of this dark matter. This has led some physicists to propose a radical alternative. Maybe our equations of gravity are simply wrong on the vast scales of galaxies and beyond. This is the heart of modified Newtonian dynamics, or MUND, proposed by physicist Mordechai Milgrom in the 1980s. MUND suggests that gravity doesn't behave exactly as Newton or Einstein said it does at extremely low accelerations, like those experienced in the far reaches of a galaxy. Instead of requiring dark matter, MUND introduces a simple tweak to the math, a new constant that defines a threshold acceleration. Above this threshold, gravity behaves normally. But below it, gravity becomes stronger than expected, providing the extra pull needed to keep those fast-moving outer stars from flying away. Astonishingly, this simple modification accurately predicts the rotation curves of a huge variety of galaxies without needing any invisible matter. It's a compelling idea, but one that struggles to explain all the evidence for gravitational phenomena that still seem to require some form of dark matter, like the behavior of colliding galaxy clusters. Now take this concept of mutable gravity and expand it to a multiverse scale. If gravity's behavior can be modified by a simple constant in an equation, what's to say that constant is the same everywhere? In a vast, possibly infinite cosmos, the parameters of modified gravity theories could themselves vary. This gives rise to a breathtaking vision of a gravitational multiverse. Imagine vast domains of space where the moment acceleration constant is set to a different value. In one domain, it might be lower than in our universe. Here, the modified gravity effect would kick in even closer to the centers of galaxies, making gravity exceptionally strong across entire galaxies. Stars would orbit at blinding speeds, and solar systems might be crushed by the intense pull, making the formation of life as we know it impossible. In another domain, the constant could be set much higher. In this place, gravity would never enter its strengthened phase. It would remain Newtonian even on the grandest scales, but without dark matter, this would be a catastrophic weakness. Galaxies would never have formed properly. They would have spun themselves apart eons ago, leaving behind a lonely, diffuse cosmos of isolated stars and gas. A dark and empty universe where gravity is too feeble to build the grand structures we see. Another compelling modified gravity idea is emergent gravity, proposed by physicist Eric Verland. In this radical view, gravity is not a fundamental force. It doesn't exist on the most basic level of reality. Instead, it emerges. It arises from the interactions of countless microscopic degrees of freedom, much like how the pressure and temperature of a gas emerge from the chaotic motion of its individual molecules. In this theory, what we perceive as gravity is actually an entropic force, a side effect of the universe's natural tendency to increase disorder. The presence of matter disturbs this underlying microscopic structure, and gravity is the system's response, a push towards a state of higher entropy. This framework also does away with the need for dark matter, as the apparent extra gravity holding galaxies together is explained by this emergent entropic effect. Apply this to a multiverse and the possibilities become even more profound. If gravity is emergent, then its properties depend entirely on the nature of the underlying microscopic reality from which it springs. Different universes could be built on completely different foundational layers. In one universe, the microscopic structure might be incredibly dense and active, leading to a very strong emergent gravity. This would be a universe of crushing densities where black holes are common and the cosmos is locked in a violent, short-lived struggle between matter and gravity. Another universe might have a sparse, sluggish underlying structure. Here, gravity would be a faint, almost negligible force. Objects would barely attract one another, planets would not form around stars, and the very concept of orbit would be meaningless. It would be a universe of lonely, drifting embers, where the force that gives our cosmos its structure and rhythm is little more than a whisper. This multiverse isn't just about gravity having different strengths. It's about gravity having different origins, emerging from unique fundamental substrates in each cosmic domain, making some universes bound by a force we would recognize, and others governed by a ghostly, ethereal pull utterly unlike anything we could ever experience. From the idea that gravity itself might be an emergent and variable force, we turn to a theory that grounds the multiverse not in exotic physics or higher dimensions, but in one of the most fundamental and universal principles governing all of reality: the relentless, irreversible rise of disorder. This is the multiverse born from thermodynamic considerations, a concept that uses the trusted laws of heat and energy to ask a profound question about our own cosmic origin, and suggests that the answer might lie in a vast, interconnected system of universes, all bound by the same inexorable rules of entropy. To understand this, we must first confront the most puzzling and underappreciated mystery in all of cosmology: the low entropy past. Entropy is essentially a measure of disorder, of how spread out energy is in a system. The second law of thermodynamics states that the total entropy of an isolated system always increases over time. Things move from order to disorder, from concentrated energy to diffuse energy. We see this everywhere. A hot cup of coffee cools to room temperature, a drop of ink disperses in water, a scattered deck of cards never spontaneously sorts itself. The universe itself is the ultimate isolated system, and its entropy is constantly increasing, driving the arrow of time we all experience from past to future. But here's the colossal puzzle. If entropy is always increasing, then to have the high entropy we see today, the universe must have started with incredibly low entropy. The early universe, just after the Big Bang, was an unfathomably hot, dense, and, this is the key part, exquisitely ordered state. All the matter and energy we see today in hundreds of billions of galaxies was packed into a volume smaller than a single atom, yet it was not a chaotic mess. It was a state of extremely smooth, uniform density, a configuration so incredibly specific and unlikely that it's like finding a perfectly stacked house of cards in the middle of a hurricane. This is the ultimate free lunch that the universe seems to have given us, and physicists have struggled for over a century to explain why the universe began in such a spectacularly special, low-entropy condition. It is the foundational reason we have an arrow of time at all, and its origin is arguably the deepest question in all of science. This is where the multiverse concept offers a stunning and elegant resolution. What if our universe's low-entropy beginning isn't a bizarre, one-off miracle, but a natural and inevitable consequence of being part of a much larger thermodynamic system? Imagine the entire multiverse as a single, colossal closed system, obeying the second law. Its total entropy is always increasing. Now, within this greater multiverse, individual universes like our own can be thought of as temporary fluctuations. In any system where entropy is generally high, there will always be small, random, and temporary decreases in entropy statistical hiccups. In a box of air, all the molecules might randomly cluster in one corner for a split second. In an infinite multiverse, a fluctuation can be the birth of an entire low-entropy universe. Our Big Bang, in this view, was not the absolute beginning. It was a local, random dip in entropy within a much larger and older multiverse that has an overall high entropy. We are that statistical fluctuation, a brief eddy of order in a vast and ultimately disorderly ocean. This perspective completely reframes the question. We no longer have to ask, why did the universe begin with low entropy? Instead, we ask, given an eternal and vast multiverse where entropy is generally high, isn't it statistically inevitable that some regions will temporarily fluctuate into a state of low entropy? The answer is a resounding yes. In fact, an infinitely old multiverse would produce an infinite number of such fluctuations. Some would be tiny and short-lived, perhaps creating a universe that lasts only a microsecond before dissolving back into chaos. Others, by pure chance, would be larger and more stable, allowing for a long and complex cosmic evolution like our own. We don't live in a special universe, we live in a survivable one, a fluctuation that was just large and ordered enough to allow galaxies, stars, planets, and ultimately us to form before it eventually succumbs to the inevitable heat death. This thermodynamic multiverse also allows for a breathtaking variety of arrows of time. In our universe, the arrow of time points in the direction of increasing entropy. But what if another universe fluctuated into existence with a different initial configuration? There could be universes where the arrow of time is reversed relative to ours. From our perspective, such a universe would appear to be moving from disorder to order. Shattered glasses would reassemble, light would pour into stars instead of radiating out, and beings would remember the future and anticipate the past. And from their perspective, our universe would be the one moving backward in time. Even more intriguing is the possibility of universes with no clear arrow of time at all, or with multiple, complex arrows emerging from their unique initial conditions. The thermodynamic multiverse is not just a collection of different physical laws, but a tapestry of different temporal experiences, all governed by the same simple, profound rule that disorder, on the whole, must always win. And so we arrive at the final, and in many ways the most profound stopping point on our journey, a concept so all-encompassing that it doesn't just add another universe to the list, but instead weaves every single theory we've explored into a single, staggering tapestry of existence. This is the ultimate multiverse ensemble, the idea that every possible form of reality, governed by every possible set of rules, doesn't just exist in isolation, but coexists in a grand meta-structure that represents the absolute totality of everything that is logically possible. It's the multiverse to end all multiverses, a framework where the branching worlds of quantum mechanics, the bubbling domains of eternal inflation, the mathematical structures of Tegmark's Level IV, the colliding brains of M-theory, and the simulated realities of the computer hypothesis are not competing ideas, but are all simultaneously true, each describing a different neighborhood within infinite cosmic metropolis. Imagine this not as a collection of separate theories, but as a vast multidimensional atlas. In one district of this ultimate ensemble, the many worlds interpretation holds sway, a realm of perpetual fission where every quantum decision spawns a new timeline, creating an ever-expanding tree of alternate histories and futures. Right next door, the bubble universes of eternal inflation float in an endless sea of false vacuum, each pocket frozen with a random lottery ticket of physical constants, some barren and dark, others blazing with stars and life. Meanwhile, in a region where the very concept of space is different, parallel membranes drift through a higher dimensional bulk, their gravity subtly tugging on each other, their collisions perhaps sparking new cosmic cycles. And in another quarter of this ensemble, reality is not made of particles but of pure information, with advanced civilizations running conscious simulations inside vast quantum computers, creating layers upon layers of virtual worlds. This ultimate ensemble doesn't force us to choose one theory over another. It proclaims that they are all valid descriptions of different sectors within a greater whole. The rules of the game change depending on where you are, but the game of existence is being played everywhere in every conceivable way. This synthesis is more than just a convenient way to settle scientific debates. It provides the most coherent answer to the deepest question that has echoed through our entire exploration. Why this universe? Why do we find ourselves in a cosmos with 3 dimensions of space, one of time, and a specific, life-permitting set of physical constants? The ultimate ensemble offers a breathtakingly simple answer, because every other possible configuration also exists. We do not live in a special or finely tuned universe. We live in one that is merely self-consistent and complex enough to allow conscious observers like us to arise and ask the question. The conditions here are not a miracle. They are a statistical inevitability in a reality so vast that the word infinite feels inadequate. The universe isn't fine-tuned for life. Life is simply what happens in the corners of the multiverse where the tuning is right. This perspective transforms our place in the cosmos from a central character in a single story to a brief, conscious flicker in one chapter of a library that contains every story that has ever been or could ever be written. The philosophical implications of this final theory are quite simply the most expansive we can possibly entertain. It means that every version of you that you can possibly imagine, and countless more that you cannot, is real somewhere in the ensemble. There is a universe where you made every different choice. There is a universe where the laws of physics are so alien that a version of you is a being of pure energy, or a pattern in a mathematical equation, or a character in a simulation designed by a long-vanished civilization. It means that every historical path was taken, every tragedy was averted somewhere else, and every dream was realized in another reality. This is not a call for nihilism, but for a profound and humbling awe. The weight of our choices is not lessened because other versions of us chose differently. It is deepened by the understanding that our path is our own, a unique thread in an impossibly vast and beautiful tapestry. We are not insignificant because the multiverse is large. We are remarkable because we are a part of it, a localized knot of consciousness capable of marveling at its own existence and daring to map the immensity that contains it. This ultimate vision of reality is the final frontier of human curiosity, a testament to our relentless drive to look into the darkness and not just see empty space, but to imagine every possible light that could ever shine within it. And so we find ourselves at the end of this cosmic odyssey, having ventured through 30 different gateways into the unimaginable. We've wandered through the infinite branching corridors of the quantum many worlds where every choice spawns a new reality. We've floated in a sea of bubble universes, each with its own unique laws of physics, born from the eternal churn of inflationary space. We've stood before the staggering landscape of string theory, with its 10 to the 500th power possible universes, and contemplated the ultimate abstraction of the mathematical universe hypothesis, where every consistent equation is a real physical world. We've been holograms projected from a distant two-dimensional surface, and characters in a simulation run on a computer of godlike power. We've been both the volunteer in the quantum suicide experiment and the observer mourning them, forever separated by the branching of our own consciousness. We've lived inside black holes and seen our entire cosmos as a single slice in a higher dimensional loaf of brains. We've watched universes evolve through cosmic natural selection, competing to create the most offspring, and we've considered the philosophical absolute of modal realism, where every possible world is concretely real. From the granular quantum foam of spacetime to the digital bits of a cosmic computer, from the seething plasma of an eternal cosmos to the pure network of cause and effect, we've explored a spectrum of ideas so vast it defies belief. Yet the true wonder is that these are not just the wild speculations of science fiction. They are serious, albeit speculative, extensions of our most successful scientific theories, each one a legitimate attempt to solve the deepest mysteries of our existence. What this incredible journey reveals is that our understanding of reality is undergoing a revolution more profound than any in human history. We are being forced to abandon the comforting idea of a single, unique universe and accept that we might be living in a reality of literally cosmic proportions, a multiverse in which our familiar home is just one page in an infinite library. This doesn't diminish our significance, it elevates our curiosity. We are the part of the cosmos that has awoken and begun to question its own nature, to map the edges of its own possibility. This conversation is far from over, it's just beginning, and now we want to hear from you. Which of these theories captivates your imagination the most? Does the quantum immortality of the many worlds interpretation send a chill down your spine? Does the elegant fine-tuning of the anthropic principle within an infinite multiverse feel like a satisfying answer? Or does the sheer, boundless possibility of the mathematical universe hypothesis fill you with a sense of awe? Let us know in the comments below, share your thoughts, and let's keep this most magnificent of discussions going. If your mind is buzzing with the possibilities of what might lie beyond the edge of our reality, you're in the right place. This channel is dedicated to exploring the furthest frontiers of science, philosophy, and wonder. To make sure you don't miss our next journey into the unknown, hit that subscribe button and ring the notification bell. The cosmos is vast, mysterious, and full of secrets waiting to be uncovered. Let's go find them together.